Hi, my name is Sean, and today I'm presenting the results from an assignment to build a model that predicts the electrical energy output of a combined cycle power plant using both operational and environmental data. For this exercise, I chose to use Vertex AI to help me build my model and to validate the model. I then compared two trained models in Vertex AI to identify which of these models provided the most accurate predictions. The goal of this exercise was to build a machine learning model to predict the electrical energy output of a combined power cycle plant by forecasting megawatt output with high accuracy. This would enable plant operators to potentially lower operational costs, reduce emissions, and improve asset utilization. The target variable in my model was net energy output measured in megawatts. In terms of data and features, the model was trained on historical operational and environmental data, which included ambient temperature, exhaust vacuum, ambient pressure, and relative humidity. As I mentioned earlier, I did train two models. Version 1 used all of the features I just mentioned, while version 2, I did remove ambient pressure and relative humidity after discovering that Vertex's AI's feature attribution scores identified them as having the lowest importance for driving predictions. So I was curious to see if by removing those two features, whether that would change the accuracy of the predictions. Again, the modeling approach involved a supervised regression task to tackle the problem. I used Vertex AI's AutoML tables, which automated much of the heavy lifting involved in model development while still giving visibility into model performance. Training, validation, and test sets were created automatically by AutoML to ensure appropriate splits of the data. In terms of evaluating model performance, AutoML does offer out-of-the-box evaluation metrics ideal for regression tasks, such as root mean square error, or RMSE, to capture large errors, which can be costly in predicting models for energy outputs. Other metrics tracked were mean absolute error, or MAE, representing the model's average prediction error, mean absolute percentage error, or MAPE, is another metric that uses percentages to explain results, which can be helpful for conversations with non-technical stakeholders. For example, you could state, on average, the model is off by X percent. The last metric I will point out is R squared, which explains the degree to which the model explains the variability of energy output. Here are the evaluation results. Version 1 achieved an MAE of 13.35 megawatts compared to version 2, which achieved 20.5 megawatts. MAPE increased from 2.92% to 4.5%, and RMSE jumped from 13.87 to 20.89. Interestingly enough, R squared stayed constant at 0.95 or 95%, which shows that both models explain the same proportion of variance, but version 2 had a much larger prediction error. This highlights why relying only on R squared can be misleading. In terms of my conclusion, the conclusion is clear between the two versions in terms of which ones provided the most accuracy. Version 1 outperformed version 2 on all error-based metrics, removing AP and RH degraded performance significantly. suggesting that even low attribution features may provide subtle or complementary information to the model, which could be helpful with predictions. This is a good reminder that the feature attribution scores should be used alongside validation testing before considering removing variables from your model. Going forward, I strongly recommend keeping all of the features in the dataset and explore more robust feature selection methods, as well as testing engineered features such as lagged environmental data to capture any delayed effects. Once deployed, the model should be monitored for drift and retrained periodically to maintain accuracy. In summary, Vertex AI helped me quickly identify that the full feature model was more accurate and reliable for predicting PowerPlant output. By validating changes before deploying them, you can ensure that the model will deliver tangible operational value. That concludes my presentation for today. Thank you.